We want to begin with a titration example that just reminds you how to use titration data to determine the concentration of an analyte in an unknown solution. And we're going to stick with the system that we've been describing where we titrate a weak acid, acetic acid, chemical formula C2H4O2, with sodium hydroxide. And so our chemical reaction is 1 mole of acetic acid reacts with 1 mole of hydroxide to produce 1 mole of acetate and 1 mole of H2O. I'm expressing this with a net ionic equation here, but you could use a balanced molecular equation to express the same acid-base reaction if you wish. But the key thing to keep in mind here is that in this titration reaction, our acid, acetic acid, is monoprotic, and our base, sodium hydroxide, can accept 1 proton. So the acid has 1 proton to transfer, the base can accept 1 proton. The stoichiometry of the reaction is 1 mole of the acid reacts with 1 mole of the base to produce 1 mole of water. And this is going to be key for the process because much like gravimetric analysis, titration is all about stoichiometry. The fundamental difference is in any given titration, you usually have 3 pieces of data. You know the exact concentration of the titrant, that is the 0.2 molar sodium hydroxide. You know how much of the titrant had to be added to the original acid sample to reach the endpoint. In this case, we had to add 50 mils of sodium hydroxide solution to reach the endpoint. We sometimes refer to this as the endpoint volume. And we need to know the volume of the original acid sample solution, which was 25 milliliters. So these are the 3 pieces of data we usually get from a titration experiment. And the strategy for calculating or determining the concentration of the analyte in a titration based on the titration data is usually fairly similar in every titration. We're going to take the concentration of the titrant, multiply it by the volume of the titrant delivered to figure out how many moles of the titrant we had to add to complete the reaction. Then we're going to use the stoichiometry of the balanced equation to figure out how many moles of the acid must have been in the original unknown. Lastly, we're going to divide by the original volume of the unknown acid sample to determine the concentration of the acid in the original sample. So again, each individual piece, not too tough. I hope it makes sense to you. I hope it rings some bells, but you have to think through carefully and make sure you're understanding the steps in the process. So our first step, I'm going to describe it here. And again, if you've been doing titrations for a while, there are quicker ways to do it, but I'm going to be very explicit in this example. First, I want to figure out how many moles of hydroxide, how many moles of the titrant I had to deliver to get the reaction to go to completion. So to do that, I take the endpoint volume in liters rather than milliliters and multiply it by the concentration of the titrant. So the concentration of the titrant is 0.200 molar hydroxide. I multiply by 0.050 liters, that's 50 milliliters. But my volume has to be in liters here to cancel with the liters unit in the denominator of the molarity. And I see that it took 0.010 moles of hydroxide to get the reaction to go to completion or to reach the endpoint. Now, because the reaction is 1 mole of the base reacts with 1 mole of the acid, there must have been 0.010 moles of the acetic acid in the original sample because the stoichiometry of the reaction is 1 to 1. So now I know that in my original sample there were 0.010 moles of acetic acid. Lastly, to get my original analyte concentration, all I have to do is divide by the volume of the acid unknown in liters. So take the 0.010 moles of the acetic acid and divide by 0.0250 liters. The original concentration of the acid must have been 0.400 molar. We're entitled to 3 sig figs because we had 3 sig figs in the molarity of the sodium hydroxide. So hopefully these steps look pretty straightforward to you, but don't underestimate a titration problem. In general, almost all titrations that you do will boil down to this strategy where you use volume of the titrant, concentration of the titrant to find the moles of the titrant needed to reach the endpoint. From that, you use the reaction stoichiometry to calculate the moles of the analyte, divide by the original volume of the analyte to get your analyte concentration. The trick is usually deciphering which piece of information is which, particularly when you're working a word problem like this. And as the titrations get a little more complex, the reaction stoichiometry may also get a little more complex. So you need to watch out for that.